ಕರ್ನಾಟಕ ರಾಜ್ಯ ವಿಜ್ಞಾನ ಮತ್ತು ತಂತ್ರಜ್ಞಾನ ಪ್ರೋತ್ಸಾಹಕ ಸೊಸೈಟಿ KSTePS ಇವರ ಒಂದು ವತಿಯಿಂದ ನಾವು ಅಕ್ಟೋಬರ್ ಮಾಹೆಯಿಂದ ಈ ವೆಬಿನಾರ್ ಕಾರ್ಯಕ್ರಮಗಳನ್ನ ಪ್ರತಿ ವಾರ ನಾವು ಹಮ್ಮಿಕೊಂಡು ಬರ್ತಾ ಇದ್ದೀವಿ. ಪ್ರತಿ ಮಾಹೆಯು ಒಂದೊಂದು ಥೀಮ್ ಮೇಲೆ ನಾವು ಮಾಡ್ತಾ ಇದ್ದೀವಿ. ಡಿಸೆಂಬರ್ನಲ್ಲಿ ಖ್ಯಾತ ಗಣಿತ ತಜ್ಞರಾದಂಥ ಶ್ರೀ ರಾಮಾನುಜಂ ಅವರ ಒಂದು ಜನ್ಮದಿನಾಚರಣೆ ನಾವು ಆಚರಣೆ ಅಂಗವಾಗಿ ಡಿಸೆಂಬರ್ ಮಾಹೆಯಲ್ಲಿ ನಾವು ಈ ಗಣಿತದ ವಿಷಯ ಬಗ್ಗೆ ಥೀಮನ್ನ ಮಾಡಿಕೊಂಡು ಈ ಗಣಿತ ಸಂವಹನಕಾರರು ಮತ್ತು ಗಣಿತ ವಿಷಯದಲ್ಲಿ ಬಹಳಷ್ಟು ಪರಿಣಿತಿಯನ್ನ ಉಳ್ಳವರನ್ನ ನಾವು ಇಲ್ಲಿ ಕರೆಸಿ ಉಪನ್ಯಾಸಗಳನ್ನ ನೀಡ್ತಾ ಇದ್ದೀವಿ. ಈ ಮುಖ್ಯವಾಗಿ ಈ ಗಣಿತ ಅಂತಕ್ಕಂಥದ್ದು ಬಹಳಷ್ಟು ಈ ವಿದ್ಯಾರ್ಥಿ ದಿಶೆಯಲ್ಲಿ ನನಗೂ ಬಹಳಷ್ಟು ಕಾಡಿದಂತಹ ಒಂದು ವಿಷಯ. ಯಾಕಂದ್ರೆ ಗಣಿತ ಅಂದ ತಕ್ಷಣ ಸ್ವಲ್ಪ ಅದು ನಮಗೆ ಕಬ್ಬಿಣದ ಕಡಲೆ ಏನೋ ಅಂತ ಅನಿಸ್ತಾ ಇತ್ತು. ಆದ್ರೆ ಯಾವಾಗ ಗಣಿತವನ್ನು ನಾವು ಬಹಳಷ್ಟು ಅರ್ಥ ಮಾಡ್ಕೊಂಡು ಅಲ್ಲಿ ಇರತಕ್ಕಂತಹ ಪ್ರಿನ್ಸಿಪಲ್ಸ್ ಗಳನ್ನ, ತತ್ವಗಳನ್ನ, ನಾವು ಸಿದ್ಧಾಂತಗಳನ್ನ ಕರೆಕ್ಟ್ ಆಗಿ ಅವುಗಳನ್ನ ನಾವು ಅರ್ಥ ಮಾಡ್ಕೊಂಡು ರೂಢಿಯನ್ನು ಮಾಡಿದ್ರೆ ಗಣಿತ 100ಗೆ 100 ಸ್ಕೋರ್ ಮಾಡ್ತಕ್ಕಂತ ಒಂದು ಸಬ್ಜೆಕ್ಟ್ ಅಂತಕ್ಕಂಥದ್ದನ್ನ ನಮ್ಮ ಅನುಭವಗಳು ಹೇಳಿದಾವೆ. ಸೊ ಇಲ್ಲಿ ಮುಖ್ಯವಾಗಿ ಈ ಗಣಿತ ವಿಷಯಗಳನ್ನ, ಯಾವ ಕ್ಲಿಷ್ಟಕರ ವಿಷಯಗಳನ್ನ ಅವುಗಳನ್ನ ಸರಳ ಭಾಷೆಯಲ್ಲಿ ಎಲ್ಲರಿಗೂ, ಅದರಲ್ಲೂ ಮುಖ್ಯವಾಗಿ ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ಮನ ಮುಟ್ಟುವ ಹಾಗೆ, ಅರ್ಥೈಸುವ ಹಾಗೆ ಹೇಳ್ತಕ್ಕಂಥದ್ದು ಏನು ಕಲೆ ಇದೆ ಅದು ಬಹಳಷ್ಟು ವಿಶಿಷ್ಟವುಳ್ಳ ಗಣಿತ ಸಂವಹನಕಾರರಿಗೆ ಮಾತ್ರ ಬಂದಿದೆ. ಸೊ ಈ ಒಂದು ವಿಷಯದ ಕುರಿತು ನಾವು ಡಾಕ್ಟರ್ CS ಯೋಗಾನಂದ್ ಅವರು, ನಮ್ಮ ಪ್ರೊಫೆಸರ್ ಆಫ್ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್, ಈಗ ರಿಟೈರ್ಡ್ ಆಗಿ ಮೈಸೂರಲ್ಲಿ ಇದ್ದಾರೆ. ಇವರು ಇವತ್ತಿನ ದಿವಸ ರಾಮಾನುಜಂ ಮತ್ತು ಪಾಯ್ ಈ ಒಂದು ವಿಷಯದ ಬಗ್ಗೆ ಬಹಳಷ್ಟು ವಿಷಯಗಳನ್ನ ನಮ್ಗೆಲ್ಲರಿಗೂ ಇವತ್ತು ನೀಡೋರಿದ್ದಾರೆ. ಅವರನ್ನ ನಾನು ನಮ್ಮ ಇಲಾಖೆ ಪರವಾಗಿ ಮತ್ತೊಮ್ಮೆ ಸ್ವಾಗತವನ್ನ ಕೋರ್ತೇನೆ. ಅದೇ ರೀತಿ ಇವತ್ತಿನ ಜೂಮ್ ಮತ್ತು ಯೂಟ್ಯೂಬ್ ಲೈವ್ ಮತ್ತು ಫೇಸ್ಬುಕ್ ಲೈವ್ ನಲ್ಲಿ ಬಹಳಷ್ಟು ಶಿಕ್ಷಕ ವೃಂದ, ವಿದ್ಯಾರ್ಥಿಗಳ ವೃಂದ ಮತ್ತು ಗಣಿತ ಆಸಕ್ತರು ಸಹ ಇಲ್ಲಿ ಭಾಗವಹಿಸಿದ್ದಾರೆ. ಅವ್ರಿಗೂ ಸಹ ನಾನು ನಮ್ಮ ವಿಜ್ಞಾನ ಮತ್ತು ತಂತ್ರಜ್ಞಾನ ಇಲಾಖೆಯ ಪರವಾಗಿ ಸ್ವಾಗತವನ್ನ ಕೋರ್ತಾ, ಈಗ ಡಾಕ್ಟರ್ ಯೋಗಾನಂದ್ ಅವರು ತಮ್ಮ ವಿಷಯವನ್ನ ಮಂಡನೆ ಮಾಡ್ತಾರೆ. ಯಾರೇ ಆದ್ರೂ ವಿಷಯಗಳ ಬಗ್ಗೆ ನಾವು ಏನಾದ್ರೂ ಕ್ಲಾರಿಫಿಕೇಶನ್ಸ್ ಗಳನ್ನ, ಸಂದೇಹಗಳನ್ನ ನಾವು ಸರಿಪಡಿಸ್ಕೋಬೇಕು ಅನ್ನೋದಿದ್ರೆ ದಯವಿಟ್ಟು ತಾವು ಚಾಟ್ ಬಾಕ್ಸ್ ನಲ್ಲಿ ಅದನ್ನ ಟೈಪ್ ಮಾಡಬಹುದು, ಅಥವಾ ಕೊನೆಯ ಹಂತದಲ್ಲಿ ನಾವು ಈ ಡಿಸ್ಕಷನ್ ಏನ್ ಇಟ್ಕೊಳ್ತೀವಿ ಅಲ್ಲೂ ಸಹ ತಾವು ಚರ್ಚೆ ಮಾಡಿ ಸಂದೇಹಗಳನ್ನ ಪರಿಹಾರ ಮಾಡ್ಕೋಬೇಕು ಅಂತ ಕೇಳ್ಕೊತಾ ಮತ್ತೊಮ್ಮೆ ನಾನು ಯೋಗಾನಂದ್ ಅವರ ಸ್ವಾಗತ ಮಾಡಿ ಈಗ ಡಾಕ್ಟರ್ ಯೋಗಾನಂದ್ ಅವರಿಗೆ ನಾನು ಮೈಕ್ ಅನ್ನ ಹ್ಯಾಂಡ್ ಓವರ್ ಮಾಡ್ತೇನೆ. ಥ್ಯಾಂಕ್ ಯು ಸರ್.
ಧನ್ಯವಾದಗಳು.
Sir, before you actually start the talk, I would like to introduce you, sir. Before you do that, Dr. CS Yogananda obtained his PhD in 1990 from the Institute of Mathematical Sciences, Chennai, under the guidance of renowned number theorist Professor R. Balasubramaniam. After his PhD, he spent 2 years in Punjab University. And Dr. Yogananda's research interests are in the areas of number theory, especially algebraic number theory, modular forms, and elliptical curves. So he is interested in mathematics teaching at all levels, from school level to advanced level. He was active in the Mathematical Olympiad program in India from 1989 to 2003 and was involved in the training and selection of the Indian team to International Maths Olympiad. In 2005, he moved to Sri Jayachamarajendra College of Engineering, Mysore, to pursue his passion for teaching in undergraduate program. He is very interested in the interface of mathematics and technology and has contributed to many IT tools of Indian languages. He was a founder editor of Samasya, a triannual journal for school students, and was a member of the editorial board of Resonance, a journal for science education published from the Indian Academy of Sciences, Bangalore. He is the author of several research and survey articles in various journals. Besides mathematics, he is interested in the classical music and mountaineering. So we are very happy to have you in this webinar program, sir. So I would like you to start with your talk. Thank you.
Thank you very much. I shall I hope it's visible.
Yes, sir. It is visible.
Okay. So the topic I have chosen is Ramanujan and pi.
ಸರ್ ತಾವು ಫುಲ್ ಸ್ಕ್ರೀನ್ ಮಾಡಬಹುದು ಅದನ್ನ.
ಇದು ಫುಲ್ ಸ್ಕ್ರೀನ್ ಅಲ್ಲಿ ಇದೆ, ಇನ್ನೂ ಆಗ್ಬೋದು. So Ramanujan and pi is the title of the talk. So there is a stamp and a postcard picture of Ramanujan with a very famous construction which I am going to show you during the presentation. And here is the constant, well-known constant pi, which has never ceased to amaze people and continues to interest deep mathematicians as well as many cranks. They come up with various theories about pi. So the two personalities, I call pi also as a personality because it seems to have some life of its own. ಈ ಎರಡೂ ಪರ್ಸನಾಲಿಟಿಗಳನ್ನು ಈ ಟೈಟಲ್ ಹಾಕಿರೋರು ರಾಮಾನುಜನ್ ಅಂಡ್ ಪೈ. ದೇ ಶೇರ್ ಮೆನಿ ಕಾಮನ್ ಟ್ರೈಟ್ಸ್. ಬೋತ್ ಆರ್ ಮಿಸ್ಟೀರಿಯಸ್ and at first they were thought to be just irrational. ಇದೊಂದು ಸ್ವಲ್ಪ ಮ್ಯಾಥಮೆಟಿಕಲಿ ಇನ್ವಾಲ್ವ್ಡ್ ಜೋಕ್ ಇದು. ನಂಬರ್ಸ್ ಅಲ್ಲಿ ಇರಾಷನಲ್ ನಂಬರ್ಸ್ ಅಂತ ಬರುತ್ತೆ. ಆ ಇರಾಷನಲ್ ನಂಬರ್ಸ್ ಅಲ್ಲೂ ಕೂಡ ದೇ ಆರ್ ನೋನ್ ಆಸ್ ಆಲ್ಜಿಬ್ರಾಯಿಕ್ ಅಂಡ್ ಟ್ರಾನ್ಸೆಂಡೆಂಟಲ್ ನಂಬರ್ಸ್. ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ √2 is irrational number, but it is not transcendental, it's algebraic. Whereas E, pi are all irrational as well as transcendental. So people, Ramanujan also, they thought he was just a cranky person, just doing something on his own, etc. And later they realized that just as pi was proved to be transcendental about 150 years ago, Ramanujan also was realized that he was a very mathematician of very deep level. So both have tendency to show up in unsuspected places. ಏನೋ ಮಾಡ್ತಾ ಇದ್ದಾಗ ರಾಮಾನುಜನ್ ಬರುತ್ತೆ, ಇಲ್ಲೆಲ್ಲೋ ಪೈ ಬರುತ್ತೆ. ಫಿಸಿಕ್ಸ್ ಏನೋ ಓದ್ತಾ ಇರ್ತೀವಿ, ಸಡನ್ಲಿ ಯು ಕ್ವಾಂಟಮ್ ಮೆಕ್ಯಾನಿಕ್ಸ್ ಫಾರ್ಮುಲಾ, pi will come out. You will not see it because pi we are usually associated with it as in a circle, area of a circle. But suddenly it shows up in quantum mechanics, thermodynamics, chemistry. You are studying something, pi will come in, etc. And similarly, Ramanujan. Now and then you suddenly hear Ramanujan. Everybody thought was a pure number theorist, and his work is only of interest to mathematicians. But suddenly, when computers, internet security, and all that came up, then they started Ramanujan codes, Ramanujan graphs. They started, and in theoretical physics, number of dimensions of the universe, again string theory, Ramanujan names come. So both have a tendency to show up in unsuspected places, and both are inexhaustible sources of inspiration. Ramanujan, ever since his life, a span of only 32 years, and ever since he became known to the world, the interest in him has never waned. In fact, ಅದು ಜಾಸ್ತಿ ಆಗ್ತಾನೆ ಹೋಗ್ತಾ ಇದೆ. ಹಾಗೆ ಪೈ ತಗೊಂಡ್ರೆ ಬಹಳ ಬಹಳ ಶತಮಾನಗಳ ಹಿಂದೆನೇ, ನಮಗೆ ಅದು ಸಹಸ್ರ ವರ್ಷಗಳ ಹಿಂದೆನೇ ನಮಗೆ ಅದರ ವಿಷಯ ಗೊತ್ತು. ಆದರೂ ಇನ್ನೂ ಅದ್ರ ಬಗ್ಗೆ ಕುತೂಹಲ ಇದ್ದೇ ಇದೆ, ಇನ್ನೂ ಅದ್ರ ಬಗ್ಗೆ ಕೆಲಸಗಳು ನಡೀತಾ ಇದೆ. So let me begin with Ramanujan construction for squaring the circle, which links up the two. So squaring the circle andre problem eniತ್ತು ಅಂದ್ರೆ, given a square, a circle of certain area, you have to construct using only ruler and compass. You have to construct a square of same area. That is what is called squaring a circle. That is, given a circle of certain area A, you have to construct a square of area A. That is the A. So Ramanujan, though actually it is not possible, you can't construct it exactly by using only ruler and compass. That was proved about 200 years ago using algebraic number theory. ಆದರೆ approximations ಕೊಡ್ಬೋದು. All are approximations. Pi is also a transcendental number, never ending. We get better and better approximations. So Ramanujan has a construction for squaring the circle, which appeared in the Journal of Indian Mathematical Society, volume 5, in the year 1913, more than 107 years ago. Yeah, one page construction. So what he says is, yeah, so you take a circle PQR, with PR as a diameter, and O is the midpoint, and PO you bisected it. H is the midpoint of PO. T is point of trisection, that is OR you make it into three parts, and the part nearer to R is T. Then you draw this perpendicular TQ. Okay. Now you measure TQ, and from R you place a chord. That is, you take this radius using compass, place it here, mark off, and then identify this point S and join S, and draw OM and TN parallel to RS. This is the chord RS, and you draw it parallel. Now place a chord PK. This construction you can look at it later. I'll just explain now. PK, which is equal to PM. Again, you put your compass here, mark off this point M, and that using that distance, you mark this point K here. Okay. And draw the tangent PL equal to MN. You draw this, you take this length MN, place the tangent at P to the circle, and identify L so that PL is equal to MN. Okay. Now RL, RK, and LK you join. Cut off RC. This keep the compass at R, measure off H, and cut off this point C so that RC is equal to RH. Draw CD parallel to LK, meeting RL at D. Then Ramanujan claims the square and RD, that is RD squared, is equal to the area of the circle PQR. So if you now draw this a square with length RD, okay, and a square of that side, then that area will be equal to the area of the given circle, approximately, because exactly you cannot do. And he goes on to say how good is the approximation. It's a very, very accurate and very good approximation. And this is typically Ramanujan's way of putting it. If the area of the circle be 1,40,000 square miles, so I computed, this means the radius of the circle is about 211 miles. So if you take an area, circle of radius 211 miles, construct that circle, and then make this construction, then the RD is greater than the true length. That is, RD should be some constant times pi. So pi is the one which will give that approximation part, and the RD so will not be exactly equal to the true length, but he says the approximation is so accurate that it is greater than the true length by about an inch. So in a radius of circle of radius 211 miles, the RD will exceed the length, which is actually uses some constant times pi, by only about an inch. It is that close an approximation. So trying to prove this, etc., Ramanujan doesn't offer proof. It's this thing, but he claims and it has been verified. In fact, those who are keen on using computers, etc., who are good at that, can try to do this construction and verify. So this is the connection between Ramanujan and pi, which was one of his first papers in Journal of Indian Mathematical Society. So ಈಗ ಈ ರಾಮಾನುಜನ್ದು ಕಾಂಟ್ರಿಬ್ಯೂಷನ್ ಏನು ಪೈ ಕಂಪ್ಯೂಟೇಷನ್ ಮಾಡೋಕ್ಕೆ ಡಿಜಿಟ್ಸ್ ಅಂತ. ಸೊ ಟು ಗಿವ್ ಯು ಎನ್ ಐಡಿಯಾ ಆಫ್ ದಿ ಸಿಚುವೇಶನ್ ಹಿಸ್ಟ್ರಿ perspective. So in 1874, William Shanks took 15 years to compute pi to 527 decimal places. See, you are all familiar with the various approximations of pi, 22 by 7, 3.1415, like that. And maybe some of you may remember pi up to 30 decimal places. There is also a Sanskrit shloka which gives approximation of pi to 25 or 30 decimal places, like that. So one tries to compute using various tricks in mathematics. So in 1874, William Shanks took 15 years. There were no calculators or anything, so he had to do everything by hand and compute the pi to 527 decimal places. So actually he gave more. He gave actually 707 places, but then they found that after 527 there were errors. And that errors were found only in 1946 after computers came into it. So whereas, so that was the story in 1874. So some 140 years later, Shigeru Kondo, a Japanese mathematician, took 94 days of computer effort. Not he. He was not doing it by hand. He used computer, writing the programming, everything. And he totally took 94 days of computer hour to compute the value to 12 trillion, more than 12 trillion places. That is the perspective, 1874 to 2013. This is a graph. So 2000 we knew very little, and just the year, and by 1900 we knew about 100 plus. It started rising. 1950 it became this one slowly, and as you can see, between 1950 and 2000 it became very steep, and in the after 2000 it's very steep. So the number of approximation. Now, two things were responsible for this phenomenal development. ಅಂದರೆ ಇದು ಕಂಪ್ಯೂಟೇಷನ್ ಮಾಡಿದ digits, number of digits of pi in my ಹೇಗೆ. So there were very two major things which were responsible. One was the appearance of Srinivas Ramanujan, and next high performance computer. First Srinivas Ramanujan, both historical. He was born in 1887 and he passed away in 1920. And analytical computers were envisaged around the end of that century, around the time Ramanujan was born, and they were actually made in 1940s and 50s. They became a reality, computing machine. And after that, solid state electronics came into the field, it went very rapidly, and today we have enormous computing power. The handheld mobile phone you have, even the cheapest among them, has a huge computing capacity. So these two were responsible. How? And these were through various formulas. So in 1910s, that is 1912, 13, and 17, 18 and all, Ramanujan wrote many papers, and he found several converging series for pi. I will show some examples. And which can compute 8 decimal places with each term in the series. That is, he gave a series for pi. If you take first 10 terms, you will get some decimal places. If you include the 11th term, then the number of decimal places will increase by 8. So you include the 12th term, then you'll add another 8 decimal places, like that. Yeah? Tell me. Okay, you can ask later, so you can chat. So, since 1980s, his series have become the basis for fastest algorithms used by Yasumamsa, Kanada, the Chudnovsky brothers, and others to compute pi. Okay, so here is an example of a series for 1 over pi based on elliptic integrals among the early formulas of Ramanujan. So, I mean, to the novice, it looks very forbidding, and I can vouch for you from as a mathematician also, this looks very strange and mind-boggling. I mean, all kinds of things. The left-hand side looks very simple, 1 over pi, but the right-hand side, just take a minute to sort of look at it. 2 root 2 divided by 9801. These are all things written down by Ramanujan. And you have to sum the series from k equal to 0 to infinity, and look at this. It is 4k factorial into, this in the numerator, 1103 plus 26390 times 26,390 times k, and the denominator looks even forbidding. K factorial raised to the power 4 into 396 raised to the power 4k. So just imagine, even to write down the first term of this series is, it is 4k. K is equal to 1, so 4 factorial. 4 factorial is 24. And 11,103 plus 26,390, that you can add. Divided by this k is equal to 1, so 1 to the power 4, so that's fine. And 396 to the power 4. So I had to compute 396 to the power 4 and then divide this numerator by that number. So even writing the first term is a thing. And how did Ramanujan envisage such things was a mystery. And Gaspar used this series. Now this looks, and you can, each term here adds 8 decimal places, as I said. So if you just compute this 2 root 2 divided by 9801 times 4 into 4 factorial, 24 into this number divided by 396 to the power 4. If you compute that, you will get 3.1415 to some extent. And then next, if you add the second term, k equal to 2, then you will get another 8 decimal places. So I mean, very quickly you can say only computer can do this kind of computations. Human wise, it's very impossible. But even more mysterious is, how did Ramanujan imagine such a thing? So he had some very deep mathematics in his mind, which could see very far. And then it is like, to give you an analogy, standing in Bangalore and you are able to see Himalaya. I mean, that is the kind of insight, deep insight and vision you can say. So it's like identifying Himalayan peaks standing in Bangalore. So none of us can see, but some big person will say, oh, point in that direction, say there are hills. Then we will go all the way in the direction he showed. We go to Delhi, from there towards Himalaya, move around, and then find the peak which was seen by Ramanujan from Bangalore itself. So that is the kind of analogy. So he just said, pointed out some direction and said there is this hill. So this series, and people try to prove. And here is another variant which Chudnovsky. Chudnovsky is for brothers. So one of the brothers, or one of them was physically differently abled, and another was his brother, and both were mathematicians, and they worked together. And they did the same kind of mathematics which Ramanujan did, and used another quadratic number field, what we call, and then they came up with another formula like the previous one. Again, 1 over pi equals to 12 times this series is again minus 1 per k, that is, these terms will be alternating, plus minus 6k factorial, then a huge 3, 3, 6, 8 digit number, things like that, divided by 3k factorial, k factorial to cube, etc. So it looks fairly mind-boggling, but mathematicians have a way of handling these things. So each term here adds 14 different places. If you just compute k equal to 1, you will get a certain value of pi. And if you take the second term k equal to 2 and add, I mean k equal to 0 is the first term. If you take that and that will be one approximation. If you take k equal to 0 plus k equal to 1, it will have another 14 places extra. So it's fairly, this is what we call as fast converging. You add decimal places quickly. So the Chudnovsky brothers used this formula several times, culminating in a 1994 calculation to over 4 billion decimal places. Remember 1994, there was now computers were not as powerful as today, but then they were able to do this using that, and they computed decimals of pi to over 4 billion decimal digits. They achieved this magnificent feat working on a homemade supercomputer built in Gregory was one of the brothers, Gregory Chudnovsky, Gregory's apartment, out of parts ordered via mail order. Of course, in America, by 1994, it was already very commonplace. What we do now, Flipkart, Amazon, etc., mail order. So that was the favor by them itself, 1994, and they ordered computer parts via mail order, and then assembled it in their garage and computed this. And it's a very, very inspirational and instructional story. And the link is given here in case you are all, I think they will share the presentation and you can look at this. The Mountains of Pi is the title of the article, computing this one. And I will later tell you what is the importance of these things. This and many such series were given by Ramanujan were proved in 1987. That was Srinivas Ramanujan's centenary year. So lots of conferences were being organized, so that gave opportunity to mathematicians to look at Ramanujan's work and prove and contribute to that mathematics. Then there were another pair of brothers, Jonathan and Peter Borwein. These were more theoretical, but they also knew computer. They continued and found many more such series by the same methods. Whatever Ramanujan had suggested, they were able to. And this again, for interest sake, I have put here. They culminated in a quartic algorithm for computation of pi. Quartic algorithm means, I mean, you step degree 4, or degree 4, then 1/4 root, etc. You have this one. So if you set a not equals this, etc., and then compute this iteration, and obtain this number ak plus 1 defined this way, then this numbers converge to 1 over pi, and each iteration quadruples the number of correct digits. So if it goes by, if you have 6 digits and then ak had 6 digits decimal places, then ak plus 1 will have 24 correct digits. Next is again. So 21 iterations like that will produce a number that coincides with pi to more than 6 trillion places. This is huge number of numbers beyond our imagination. So just take it. Now my question is, I'm going to do this because there are lots of students and teachers among the audience in this way. Why are we not able to do this in India? This does not require huge factories or companies. Like, if you want to produce a Boeing aircraft, you need huge this thing and lot of raw material. But this is computing and computing power and brain. And this is one of the things which, as a teacher who has been involved in teaching for more than 30 years now, and noticing that bright students come out of it, and therefore there is no dearth of raw material of that kind. And from the government side and on board, there are 23 IITs, 31 National Institute of Technologies, 54 central universities, 7 ISERs, Indian Institute of Science, Education and Research, more than 5 advanced research institutes for mathematics. But still we have not gone anything like this kind of computation. Trillion digits of pi, 6 trillion digits of pi, or verifying them, etc. has not been done. Though the person who was responsible for this was born in India, Srinivas Ramanujan. Okay, so that's a point to ponder. Those who are young and wanting to do things should do something in this direction. Now is the critical question. So far it might have looked very complicated and why one takes it over. ಯಾತಕ್ಕೆ ಇಷ್ಟೆಲ್ಲ ಕಂಪ್ಯೂಟ್ ಮಾಡ್ತೀವಿ ಪೈ ಇದು ಅಂತ? Why this craze for computing more and more, billion digits, trillion digits? Nobody is going to use it in that, because everywhere they only use 5 or 6 places. Illi, I want to tell a curious story. Most people may think pi is not useful at all in the practical, but you will be surprised when I say pi, actually the value of pi, what will be usable value of pi, an approximation, has to be declared either in the constitution or in the Bureau of Standards, right? Like 1 liter is how much, 1 meter is how much, like that. They have to give a value of pi to some practical purposes. Okay, so this, for example, in the India, I think it is in the Bureau of Indian Standards, they will have a value of pi, because the point is pi will get involved in many actual day-to-day applications. For example, somebody might be wanting to construct a stadium. So stadium is usually either circular or elliptical in shape. So they will have to quote, the tender will have to say what is it per square feet, how much is it, etc. So when you do that, the area formula involves pi. So what value of pi do you use? So if you just use 3.14 and stop there, the contractor might put 3.1415. So it will jack up the value by a little. Then the other I put 3.14159 next decimal place, then it will again. Since the amounts involved are now big, the differences might be in few lakhs of rupees. So the contractor and the civil engineer might clash there. So okay, forget about the stadium. That's okay, a few thousands or tens of thousands or a few lakh rupees, maybe they will settle for something. But just imagine if somebody wants to redo, or like the Golden Temple of Amritsar, somebody wants to cover some dome with gold sheet, with thin gold foil, like Swarna Shikara. So lots of temples do that. So now here the material involved is gold, and again the thing is dome is roughly spherical in shape. Therefore, the area of that surface and the volume of gold, amount of gold required, is going to involve pi. So now if you make this thing, the computer might, the contractor might say, I have done this much work and my bill is this much. So the civil engineer will verify it on behalf of the temple or the government, and will say, no, you have taken a higher this thing, it's only a couple of crores less because this. Then they will find out where is the thing. The measurements are all correct. Then the contractor will have used the value, let's say 3.14159, whereas the engineer will only use 3.14. So naturally, this will be less than that. So if the amount involved is crores, now people are not going to just settle. They will go to court. Now court will have a problem. They have used the correct formula, they have done the correct measurement. Then the problem is in using different approximations for pi. So to resolve such cases, the government, every government should have declared a value of pi as a for practical purposes, like the ones I have cited. So it is important. So though you don't need billion places, because here I think any, for example, your calculators, if you press pi, will give a approximation of pi, and usually that is the one which is used by civil engineers and all, and that is the one which is. So this is one example, pi. But why billions of places, trillions of places, etc.? Okay, I will tell you something which will realize if this the kind of things had not been done. For example, digital technology would not be where you now know it to be. For example, you take your mobile phone and dial a number, that will find the correct mobile number wherever it is in the world. And that's an extraordinary thing. If the things had not been set up, all this number crunching, etc., digital technology would not have advanced that much. You dial a number and it will go to the number, and maybe 10 times you dial to get the correct one. So that's very possible. So I will tell you where that kind of things are used, and where these processors which we use in mobile phones, automobiles, and all. So this is what is called number crunching. So billions of places, trillions of places. Pi was an example. So there are other examples like finding the largest prime number. So you know prime numbers: 3, 5, 7, 11, 13, 17. You keep going, 103, then like that. So you keep going on, and bigger and bigger and bigger and primes. And so now you know 120 digits, 150 digits, 200 digits numbers, which are prime numbers. So it becomes very difficult to verify whether it's prime and confirm, etc. But that's called number crunching. Or another very famous this thing, the largest pair of 10 primes. And iದ್ರ ಬಗ್ಗೆ ಒಂದು ಕತೆ ಹೇಳ್ತೀನಿ next, and which will show the importance of this mathematics. And factorizing very big numbers. This you may not realize, but this is the basis of all your internet commerce. You go to the ATM, put your card, and it will ask you, okay, you will put your 4-digit PIN number and verify whether you are the correct owner of that credit card. So that technique of security, of identifying you, uses this called factorizing a very big number. If this had not been there, there was no internet security, and banking would not have been possible over machines. So one application of this kind of finding this largest prime number, factorizing big numbers, etc., is these serve as benchmarks for testing new microprocessors. So as you know, computers becoming more and more powerful, mobile phones also. You may have a 15 MP camera now, and then 1 week later you will suddenly see somebody announcing a 30 MP camera with the same price or less price. So my processors will be improving. When you are doing those things, you need to test them. Okay. So there is an interesting story involving twin primes, which I will sort of quickly tell you, which illustrates this importance of this. Okay. So these twin primes are prime numbers of the form 3 and 5, 5 and 7. They differ by 2. 11 and 13 are prime numbers and they differ by 17. Keep going. Now the question is, we all know there are infinitely many prime numbers. School and all nಮಗೆ ಪ್ರೂವ್ ಮಾಡಿರ್ತಾರೆ ಅದನ್ನ. ಇಲ್ಲೂ now the question is, how many twin primes? Are there finite number of only now we agree that it has a solution. People know it is. So there was an attempt to prove this twin prime conjecture, that there are infinitely many primes, by some proof is just given by Euler. So this is only for advanced people. Others can just listen to it and concentrate on what comes later. So Euler showed that one of these series of reciprocals of prime, that is, if you take 1/2 plus 1/3 plus 1/5, etc., that does not have a definite sum. It diverges. That's what we say. What that means is that if you take 100 primes and take their reciprocals and add, you get some number. And then next you go, it will become some. And you can say, okay, can I, by adding, of course, each time it will increase. How much will it increase is the question. Let me tell you what this means, divergence. It means you give me any number. You say 1 million. I can find number of primes which, so that the sum will exceed that. That's what it means. Very difficult to imagine, but that's what it means. But the series of reciprocals of twin primes converges. If it had diverged, we would have had this thing, and that is now the thing. So even though that's conjecture, so what the people were trying to do was, okay, I want to consider the reciprocals of twin primes, and I keep adding and try to find this thing. So so this is all some deep mathematics. So let me go to the story part. So there was a person, Thomas Nicely, who was doing such thing. Whenever some new twin prime is found, he would take the reciprocals, add it to the series which of already known twin primes, and then compute the next number. That was all what he was doing. Very seemingly very innocent and innocuous and completely useless activity. But in 1994, this led Thomas Nicely to discover an error in the Pentium chip. In 1993-94, Intel released what is called the Pentium chip. Till then it was 286, 386, 486 machines, they were called. 8386, 8486, 80. And next one was not, so for a brief period it was called 586, but then it was renamed as Pentium. They said it's a much more powerful processor, so the computers will become more fun. So they made it and released it, and people all around the world started using. By that time, computers were being used for many things other than just calculation. And incidentally, the story is, the point in history is that Vinod Dham, an Indian alumni of Delhi College of Engineering, was involved in the production of this Pentium chip. So it had an error, but finding that error is not easy. So Thomas Nicely, how did he find this error in the chip? It's very difficult. So he was using this to compute twin primes. So when 94, the Pentium processor came, he said, okay, this will improve my calculations. I can compute faster. And he took that. But then he started noticing that some errors were there in his computation. Then he did like a detective. He tried to trace the source of the error. Maybe I made a typing mistake. Maybe there was something else that went wrong in the computer program which was used, etc. Finally, he traced it to Pentium chip. So he says, I encountered erroneous results which were related to this bug as long ago as June 1994. But it was not until October 94 that I felt I had eliminated all other errors, and I contacted Intel tech supports regarding this bug in October. So initially there was no response from Intel, but then he shared it with many other people. They all started producing more examples. In December 1994, Intel recalled the defective processors. It's a huge. So whoever had bought a Pentium machine, they could return it. You are familiar, I suppose. ಯಾವುದೋ ಒಂದು ಕಾರ್ ಇರುತ್ತೆ, ಅದಕ್ಕೇನೋ ಡಿಫೆಕ್ಟ್ ಅಂತ ಹೇಳಿ ಯಾರ್ಯಾರು ಆ ಕಾರ್ ಕೊಂಡ್ಕೊಂಡಿದ್ದೀರಾ ಎಲ್ಲ ವಾಪಸ್ ಬನ್ನಿ, we will give you the correct parts for the corrected part for your car anta, that will be there. It's a very costly exercise. So that was done. So suppose Thomas Nicely had not found this bug, who would have found this bug? And it's very difficult to say if a bug, if it had stayed in the chip, it would have definitely made some errors for computation. For example, as I said, it would even result in a mobile phone call going to a wrong number. You dial some number and it goes to a different number. So that's kind of processor mistakes can happen. So it is not an exaggeration to say that the digital revolution may have been delayed. Digital revolution, ishtalla mobile phones, communication technology, it might have been delayed because ಈಗೆಲ್ಲ ಮೊಬೈಲ್ ಫೋನ್ ಯಾಕೆ ಕೊಂಡ್ಕೋತಾರೆ ಅಂದರೆ ನೀವು ಡಯಲ್ ಮಾಡಿದರೆ ಹೋಗುತ್ತೆ ಕರೆಕ್ಟಾಗಿ. ಬಟ್ ಸಪೋಸ್ ಯಾರೋ ಹೇಳ್ತಾರೆ ಇಲ್ಲಪ್ಪ ಅದು ನೀನು ಒಂದು 10 ಸಲ ಡಯಲ್ ಮಾಡಿದರೆ ನಿನಗೆ 2 ಸಲ ಸರಿಯಾದ ನಂಬರ್ ಸಿಗ್ಬೋದು, ಇನ್ನು 8 ವೇಸ್ಟೆಡ್ ಕಾಲ್ಸ್ ಅಂದರೆ ಪೀಪಲ್ ವಿಲ್ ಬಿ ಹೆಸಿಟೆಂಟ್ ಇನ್ ಬೈಯಿಂಗ್ ದಿ ಡಯಲ್ ಮೊಬೈಲ್ ಫೋನ್. ರೈಟ್? ಇಫ್ ಇಟ್ ವರ್ಕ್ಸ್ ವೆಲ್ ಯು ಬೈ, ಅದರ್ವೈಸ್ ಯು ಡೋಂಟ್. ಸೊ ಇಟ್ ವುಡ್ ಹ್ಯಾವ್ ಬೀನ್ ವೆರಿ. ಸೊ ಇದನ್ನು ಹಾಗಾದರೆ ಹೇಗೆ ನಾವು ಮಾಡ್ತೀವಿ ಅಂದರೆ, ಆ್ಯಂಡ್ ಆಲ್ಸೋ ಐ ಕ್ಯಾನ್ share more examples. They can be very dangerous. You have seen such things. In 1996, Ariane 5 was a space shuttle. Europe knows. It only 40 seconds after the takeoff, it exploded, killing all the people inside. They were all burned to death. And of course, our own astronaut Kalpana Chawla also lost her life in some such thing. So these things could come because of computational problem. For example, in this case, it was finally discovered that a 64-bit floating point number, I mean some advanced number this thing, but the way computer represent numbers. So it was converted to a 16-bit signed integer. And the number was larger than 32,767, the largest integer storable in 16-bit signed integer. And conversion failed, and the rocket did an unexpected thing, and it just exploded. So that is the problem. How do you test this processor? Let me just tell you briefly, because the time is running out. It's this processor means they have many inputs. They will have 1 million inputs and 1 million outputs. I mean, this is a very small processor. Otherwise, real processors there are billions of outputs. So we need to know whether these inputs and outputs are matching properly. If your new building is there, what you do is after the electrician says everything is fine, you go and put on the switches. If the light switch should switch on the correct light, the fan switch should on the fan, and they should. If a light switch you put and you expect this light, but some other light comes, you tell the electrician there is a wrong wiring. So in a building with only about, let's say 100 lights and 50 fans, you may be able to test out each combination. But if you have million inputs and billion inputs, how will you test? You can't. Very, very difficult. So what they do is, they will have computed this number of pi to trillion places. So if you bring a new processor, what they do is they use the same algorithm and use that new processor. If the computation agrees with the old value, which you have already got, which you have tested many times, then they certify that that chip also seems to work properly. So if you do it for some 3-4 different such numbers, then you certify the chip. That's why, so the moral of the story is that if you keep working sincerely on whatever it is and without bothering about its use or its market potential, etc., sometimes it might click and become very, very useful to yourself and to the society. Okay. So, I mean, the topic has become a little advanced, but I wanted to show that Ramanujan's mathematics has still got relevance and it is still useful in, I would say, day-to-day activities, because one wants to find newer and newer mobile phones, more and more powerful transmitting protocols, etc. So in all those cases, Ramanujan's work will be useful. Yeah. So thank you. This is about what I wanted to say. And in our questions, you can. And I would request the organizers, I can send it to them. And those who want can take a copy of this presentation. Thank you very much. If anyone has any questions, you can ask. There are about 10 minutes of time.
ಥ್ಯಾಂಕ್ ಯು ಸರ್. ಯಾರಾದರೂ ಪ್ರಶ್ನೆಗಳಿದ್ರೆ ಕೇಳ್ಬೋದು.
Professor Yogananda, why don't you close your screen and then you come on the video?
Oh, you want to see me? Huh? Okay. Yeah, I am there, I suppose. Yeah. You able to see me? I mean.
Hello, sir.
Yeah.
ಪ್ರಶ್ನೆ ಕೇಳಿ.
ಕೇಳಿ. Yeah, Virendra.
Hello, sir. I am Virendra S from Saptagiri College, first PU. Sir, ನಾವು ಈಗ 3.14 ಸಮಥಿಂಗ್ ಇದೆಯಲ್ಲ ಸರ್ ಪೈ ವ್ಯಾಲ್ಯೂ. ಸರ್ ಅದು 22/7 ಹಾಕಿದ್ರೆ ಪರ್ಫೆಕ್ಟ್ ವ್ಯಾಲ್ಯೂನೇ ಬರುತ್ತಲ್ಲ ಸರ್?
ಅಲ್ಲ, ಪರ್ಫೆಕ್ಟ್ ವ್ಯಾಲ್ಯೂ ಅಂತಲ್ಲ, ಅದು ಅಪ್ರಾಕ್ಸಿಮೇಟ್ ನಂಬರ್. ಅದನ್ನ ಹಾಗೆ ಹೇಳಿದೀವಿ ಅಷ್ಟೇ. ಅದರ ವ್ಯಾಲ್ಯೂ ಅದಲ್ಲ. 3.1415 ಅಂತ ಬರುತ್ತೆ. ಅದು ನೀನು ಮಾಡಿದಷ್ಟು ಇನ್ನೂ ಆಕ್ಯುರೇಟ್ ಆಗ್ತಾ ಹೋಗುತ್ತೆ. ಅದು ಒಂದು ಅಪ್ರಾಕ್ಸಿಮೇಷನ್. ತುಂಬ ಹಿಂದೆನೆ ಇದು ಆರ್ಯಭಟ ಇವರೆಲ್ಲ ಕೊಟ್ಟ ಅಪ್ರಾಕ್ಸಿಮೇಷನ್ಗಳು ಆ ಥರ ಇದೆ. ಆರ್ಕಿಮಿಡಿಯಸ್, ಆರ್ಯಭಟ ಅವ್ರ ಕೆಲಸ.
ಓಕೆ ಸರ್.
ನಮಸ್ಕಾರ, ನಂದೊಂದು ಪ್ರಶ್ನೆ ಇತ್ತು.
ಹೇಳಿ ಗಣನಾಥ್.
ಗಣನಾಥ್ ಮಾತಾಡ್ತಾ ಇರೋದು. ನೀವು ಅಲ್ಲಿ ಸ್ಟೂಡೆಂಟ್ಸ್ ಬಗ್ಗೆ ಹೇಳಿದ್ರಲ್ಲ, ಮತ್ತೆ ಎಷ್ಟೊಂದು ಇನ್ಸ್ಟಿಟ್ಯೂಷನ್ಸ್ ಇದೆ, ಎಷ್ಟೊಂದು ರಿಸರ್ಚ್ ಗ್ರೂಪ್ಸ್ ಇದೆ. ಆದ್ರೆ ನಮ್ಮ ದೇಶದಲ್ಲಿ ಯಾಕೆ ಈ ರೀತಿಯ ಕಡಿಮೆ ಖರ್ಚಾದ್ರೂ ಖರ್ಚಿನಲ್ಲೂ ಮಾಡಬಹುದಾದ್ದು, ಬಟ್ ಸ್ವಲ್ಪ ಇನೋವೇಷನ್ ಬೇಕಷ್ಟೇನೆ, ಮತ್ತೆ ಡೆಡಿಕೇಶನ್ ಬೇಕು. ಅದಕ್ಕೆ ಉತ್ತರ ಏನು? ನಾನು ಬಹಳ ವರ್ಷಗಳಿಂದ ಇದನ್ನ ನನ್ನನ್ನೇ ಕೇಳ್ಕೊಳ್ತಾ ಇದ್ದೀನಿ, ಉತ್ತರ ಸಿಕ್ಕಿಲ್ಲ.
ನನ್ನ ಅನುಭವದ ಮೂಲಕ ಹೇಳ್ಬೇಕಂದ್ರೆ, ನಮ್ಮಲ್ಲಿ ಸ್ಕೂಲ್ ಲೆವೆಲ್ ತನಕ ಬಹಳ ಚೆನ್ನಾಗಿದೆ. ಒಂಥರ ಎಜುಕೇಶನ್ದು ತುಂಬ ಜಾಸ್ತಿ ತುಂಬ್ತೀವಿ. ಆದರೂ ಅಲ್ಲಿ ಇರ್ತಾರೆ. ಈ ಅಂಡರ್ ಗ್ರ್ಯಾಜುಯೇಟ್ ಇದೆಯಲ್ಲ, BA BSc ಇವೆಲ್ಲ, ಇಲ್ಲಿ ನಮಗೆ ತೊಂದರೆ. ಈ ತೊಂದರೆ ಯಾಕಾಗ್ತಿರೋದು ಅಂದರೆ, ನಾವು ಆ PUC ಒಂದು ಇಂಪಾರ್ಟೆಂಟ್ ಜಂಕ್ಷನ್ ಅದನ್ನ ನಾವು ಜಂಕ್ಷನ್ ಅಂತ ಟ್ರೀಟ್ ಮಾಡಿಬಿಟ್ಟಿದ್ವಿ. ಇಟ್ ಈಸ್ ಲೈಕ್ ಎ ರೈಲ್ವೆ ಜಂಕ್ಷನ್. PUC ಹೋದವ್ರು ಯಾರು ಸಬ್ಜೆಕ್ಟ್ ಕಲ್ತ್ಕೊಳ್ಳೋದೇ ಇಲ್ಲ. ಅವ್ರಿಗೆ CET, IIT, JEE ಇದೇನೆ. ಅದಕ್ಕೆ ನಾನು ರೈಲ್ವೆ ಜಂಕ್ಷನ್ ಅಂತೀನಿ PUCನ. ಅಲ್ಲಿ ಬಂದರೆ ಆ ಸ್ಟೇಷನ್ನಿಂದ ಇಂಪಾರ್ಟೆನ್ಸ್ ಯಾರಿಗೂ ಗೊತ್ತಿಲ್ಲ. ಅಲ್ಲಿಂದ ಎಂಜಿನಿಯರಿಂಗ್ ಹೋಗ್ಬೇಕು, ಮೆಡಿಕಲ್ಗೆ ಹೋಗ್ಬೇಕು, ಹೀಗೇನೆ ಬಿಡುತ್ತೆ. ಅವ್ರು ಏನು ಒಂದು ಇನೋವೇಟಿವ್ ಕೆಪಾಸಿಟಿ ಎಲ್ಲ ಇತ್ತು, ಟ್ಯಾಲೆಂಟು, ಅವೆಲ್ಲ ಅಲ್ಲಿ ನಷ್ಟ ಆಗೋಗ್ತದೆ. ಅದನ್ನ ನಾವು BE-ಲಾಗ್ಲಿ BSc-ಲಾಗ್ಲಿ ನಮ್ಮ ಎಜುಕೇಶನಲ್ ಸಿಸ್ಟಮ್ಸು ಅವನ್ನ ತಿರ್ಗಾ ವಾಪಸ್ಸು ಆ ಕ್ರಿಯೇಟಿವಿಟಿ ಕಡೆಗೆ ತಿರುಗಿಸೋದ್ರಲ್ಲಿ ವಿಫಲವಾಗಿದೆ. ಇದಕ್ಕೆ ಒಂದು ಅವ್ರಿಗೆ ನಾವು ತುಂಬ ಜಾಸ್ತಿ ಕೊಡ್ತಾ ಇದ್ದೀವಿ ಫ್ಯಾಕ್ಟ್ಸ್, ಸಿಲೆಬಸ್ ಜಾಸ್ತಿ, ಅದೆಲ್ಲ ಅವರಿಗೆ ಫ್ರೀಯಾಗಿ ಥಿಂಕ್ ಮಾಡೋಕ್ಕೆ ಜಾಸ್ತಿ ಅವಕಾಶಗಳಿವೆ. ಇದು ನನ್ನ 20 ವರ್ಷದ ಒಂದು ಅನುಭವ. ಈಗ ನಾನು ತುಂಬ ಟ್ಯಾಲೆಂಟೆಡ್ ಸ್ಟೂಡೆಂಟ್ಸ್ ಜೊತೆ ವರ್ಕ್ ಮಾಡಿದೆ. ಅಲ್ಲೆಲ್ಲ ಈ ಥರ ತೋರಿಸಿ ಅವ್ರಿಗೆ ಮಾಡಿದಾಗ ನಾನು ಐ ಹ್ಯಾವ್ ಹ್ಯಾಡ್ ಸಕ್ಸಸ್. ಐ ಹ್ಯಾವ್ ಡನ್ ಸಮ್ ವೆರಿ ನೀಟ್ ಕಂಪ್ಯೂಟೇಷನ್, ಗುಡ್ ಕಂಪ್ಯೂಟೇಷನ್. ಇನ್ಫ್ಯಾಕ್ಟ್ JC ಒಳಗೆ ಬಂದಾಗ ಸ್ಟೂಡೆಂಟ್ ಹೇಳ್ಕೊಟ್ಟೆ, ಈ ರೋಟೆ ಪ್ರೋಗ್ರಾಮ್ ಒಂದು 60 ಡಿಜಿಟ್ ನಂಬರ್ ಇದ್ರೆ ಅದನ್ನು ಫ್ಯಾಕ್ಟ್ರೈಸ್ ಮಾಡ್ಬೋದಾಯ್ತು, ಆ ಥರ. ಶಾಸ್ತ್ರಿ ಅವರು?
ನನ್ನ ಹೆಸರು VS ಶಾಸ್ತ್ರಿ ಅಂತ. ನಾನು ಕೆಲವು ಸಲ ಎಲ್ಲ ಈ ಮಕ್ಕಳ ಹತ್ರ ಇಂಟರಾಕ್ಷನ್ ಮಾಡಿದಾಗ ಅವರು ಕೇಳ್ತಾ ಇದ್ರು, ಈಗಲೇನೋ ಕಂಪ್ಯೂಟರ್ ಟೆಸ್ಟ್ ಮಾಡ್ಕೋಸ್ಕರ ನೀವು ಅಷ್ಟೆಲ್ಲ ಪೈನ ಬಳಸ್ಕೊಳ್ತೀರಿ, ಹಿಂದೆ ಯಾಕೆ ನೆಸೆಸಿಟಿ ಬಂತು? ಅದು ಪೈ ಬೆಲೆನ 22/7 ಅಲ್ಲ ಅಥವಾ ಇನ್ನೊಂದು ಏನೋ ಅಲ್ಲ ಅನ್ಬಿಟ್ಟು ಹೆಂಗ್ ಗೊತ್ತಾಯ್ತು ಅವರಿಗೆ ಅಂತ ಕೇಳ್ತಿದ್ರು. ಸೊ ಅದ್ರ ಬಗ್ಗೆ ನೀವು ಸ್ವಲ್ಪ ಏನಾರ ಹೇಳಿ.
ಹೌದಾ, ನಾನು ಅದೊಂದು ಚೂರು ತೋರಿಸ್ಬೋದಾಗಿತ್ತು. ಒಂದು ತುಂಬ ಮಿಸ್ಟೀರಿಯಸ್ ಆಗಿ ಪೈನ ಹೇಳ್ಬಿಡ್ತೀವಿ, ಬಟ್ ಅದೇ ಅದರದ್ದು ವೇರಿಯಸ್ ಅಪ್ರಾಕ್ಸಿಮೇಷನ್ ಅಂತ. ಈಗ ಎಲ್ಲೆಲ್ಲಿ ನಮಗೆ ಸರ್ಕ್ಯುಲರ್ ಆಗಿರುತ್ತೋ, ಈಗ ಉದಾಹರಣೆ ಒಂದು ಗಾಡಿ ಚಕ್ರ ಮಾಡಬೇಕಾದ್ರೆ ಅದು ಸರ್ಕ್ಯುಲರ್ ಆಗಿರುತ್ತೆ. ಸೊ ನಮ್ಗೆ ಅದಕ್ಕೆ ಎಷ್ಟು ಮೆಟೀರಿಯಲ್ ಬೇಕು ಅಂತ ಅವರು ಯೋಚನೆ ಮಾಡಿ ಇದು ಮಾಡಿದಾಗ, ನೀವು 1-2 ಮಾಡೋಕ್ಕಿದ್ರೆ ಎಷ್ಟು ಮೆಟೀರಿಯಲ್ಲು ಇದೊಂದು ಮಾಡಿಬಿಡ್ಬೋದು. ಆದರೆ ಜಾಸ್ತಿ ಮಾಡಬೇಕಾದಾಗ ಎಷ್ಟು ಮೆಟೀರಿಯಲ್ ತೊಗೋಬೇಕು ಅಂತ. ಸೊ ಒಂದು 1000 ಚಕ್ರ ಪ್ರೊಡ್ಯೂಸ್ ಮಾಡಬೇಕಂದ್ರೆ ಏನು ಬೇಕಾಗುತ್ತೆ? ಇದೇ ಥರ ಸರ್ಕ್ಯುಲರ್ ಆಗಿರೋದು ಸುಮಾರಷ್ಟಿದೆ ಪ್ರಪಂಚದಲ್ಲಿ. ಅದು ಆಮೇಲೆ ಇನ್ನೊಂದು ಭಾಳ ಇದು ಅಂದರೆ ಗ್ರಹಣದ ಇದನ್ನು ಕಂಡುಹಿಡಿಯೋಕ್ಕೆ, ಯಾವಾಗ ಗ್ರಹಣ ಆಗುತ್ತೆ ಅಂತ. ಯಾಕಂದರೆ ಆಕಾಶಕಾಯಗಳ ಚಲನೆ, ಸೂರ್ಯ ಚಂದ್ರ ಇವೆಲ್ಲನೂ ಎಲಿಪ್ಟಿಕಲ್ ಆರ್ಬಿಟ್ಸೆ. ನೀವು ಅದನ್ನೆಲ್ಲ ಕಂಡುಹಿಡಿಬೇಕು ಅಂದರೆ ಪೈ ವ್ಯಾಲ್ಯೂ ಬೇಕು. ಪೈ ಅಂತ ಎಕ್ಸಾಕ್ಟಾಗಿ ಇದು ಮಾಡಿದ್ರು. ಸೊ ನೀಲಕಂಠ, ಮಾಧವ ಇವೆಲ್ಲ ಕೇರಳ ಮ್ಯಾಥಮೆಟಿಷಿಯನ್ಸು ತುಂಬ ಕೆಲಸ ಮಾಡಿದ್ರು ಈ ಪೈದು ಇನ್ಫೈನೈಟ್ ಸೀರೀಸ್ ಮೇಲೆ. ಅವೆಲ್ಲ ಮಾಡಿದ್ದು ಹೀಗೆ. ಸೊ ಈಗ ಫಸ್ಟು ಏನು ಹೇಳ್ತಿದ್ರು, ಎಕ್ಲಿಪ್ಸು 2 ಗಂಟೆಯಿಂದ 3 ಗಂಟೆ ಒಳಗೆ ಆಗತ್ತೆ ರೀ ಅಂತ. ಸೊ ನೆಕ್ಸ್ಟ್ ಇನ್ನೂ ಆ್ಯಕ್ಯುರೇಟ್ ಆಗಿ ಇಲ್ಲ, ಇದು 2:15 2:45 ಒಳಗೆ ಆಗುತ್ತೆ ಅಂತ. ಆಮೇಲೆ ಇನ್ನೂ ಆ್ಯಕ್ಯುರೇಟ್ ಆಗಿ ಈಗೆಲ್ಲ ಸ್ಪರ್ಶಕಾಲ ಅವೆಲ್ಲ ಸೆಕೆಂಡ್ಸಲ್ಲಿ ಕೊಡ್ತಾರೆ. ಇಲ್ಲಿಗೆ ಸ್ಪರ್ಶಕಾಲ ಇವೆಲ್ಲದಕ್ಕೂ ಮಾಡಬೇಕಂದ್ರೆ ನಿಮಗೆ ಪೈದು ವ್ಯಾಲ್ಯೂ ಬೇಕು. ಸೊ ಅಸ್ಟ್ರಾನಮಿ ಒಂದು ಮೇಜರ್ ಮೋಟಿವೇಟಿಂಗ್ ಫ್ಯಾಕ್ಟರ್ ಇತ್ತು. ಇನ್ನೊಂದು ಪ್ರಾಕ್ಟಿಕಲ್ ಲೆವೆಲಲ್ಲಿ ಯಾವ ಸರ್ಕ್ಯುಲರ್ ಆಗಿರೋದು, ಸ್ಪೆರಿಕಲ್ ಆಗಿರೋದು, ಅದೇ ನಾನು ಹೇಳ್ದಂಗೆ ಚಿನ್ನ ಬೆಳ್ಳಿ ಅದು ಇನ್ವಾಲ್ವ್ ಆದಾಗ ತುಂಬಾ ಬೇಕಾಗುತ್ತೆ. ಅವರು ಹೇಳಬೇಕಾದ್ರೆ ಇದು ಯಾವುದೋ ಒಂದು ನೀವು ಒಂದು ಚಿನ್ನದ್ದು ಇದನ್ನೊಂದು ಗುಂಡು ತೆಗೆದು ಮಾಡ್ತಿದ್ರೆ ಅದಕ್ಕೆ ಎಷ್ಟಾಯಿತು ಅಂದರೆ ಎಷ್ಟು ಚಿನ್ನ ಬೇಕಾಯಿತು, ಎಷ್ಟು kg ಅದಕ್ಕೆ ಅಂತ ಬೇರೆ, ಅಥವಾ ಅದನ್ನು ಕರಗಿಸಿ ನಾನೊಂದು ತಟ್ಟೆ ಥರ ಮಾಡಬೇಕು ಅಂದರೆ ಅವೆಲ್ಲದಕ್ಕೆ ಮಾಡಬೇಕಾದ್ರೆ ಬೇಕಾಗುತ್ತೆ. ಸೊ ಈ ಥರದ ಕೆಲವು ಗ್ರೌಂಡ್ ಅಪ್ಲಿಕೇಶನ್ಸ್ ಇದ್ದು ಅದಕ್ಕೆ. ಬಟ್ ಅವಕ್ಕೆಲ್ಲ 8-10 ಪ್ಲೇಸಸ್ಸು ಅದೇ ಸಾಕಾಗ್ತಾಯಿತ್ತು. ಇನ್ನೂ ಆ್ಯಕ್ಯುರೇಟಾಗಿ ಹೋಗ್ತಿದ್ದಂಗೆ ದೊಡ್ಡ ದೊಡ್ಡ ಕೆಲಸಗಳು ಮಾಡಬೇಕು ಅಂತ ಹೋದಾಗ ನಮಗೆ ಜಾಸ್ತಿ ಆ್ಯಕ್ಯುರೇಟ್ ಆಗಿರೋ ವ್ಯಾಲ್ಯೂ ಬೇಕಾಗಿದೆ.
ಇನ್ಯಾವುದಾದ್ರೂ ಪ್ರಶ್ನೆ ಇದ್ರೆ ಕೇಳಬಹುದು.
ಚಾಟ್ ಬಾಕ್ಸ್ ನಲ್ಲಿ ಒಂದು ಪ್ರಶ್ನೆ ಬಂದಿದೆ. ಜಾಹ್ನವಿ ಅಂತ ಕೇಳಿದ್ದಾರೆ, ಚಾಟ್ ಬಾಕ್ಸ್ ಗೆ ಹೋಗ್ಬೇಕು ಯೋಗಾನಂದ.
Why do we use pi for formulae like area of a circle, some 3D figures ಅಂತ ಕೇಳ್ತಾರೆ.
ಇದು ಏನಕ್ಕೆ ಅಂದ್ರೆ ಅದು ಏರಿಯಾ ಆಫ್ ಎ ಸರ್ಕಲ್ದು ಹಾಗೆ ಬರುತ್ತೆ. ಅದಕ್ಕೆ ಫಾರ್ಮುಲಾ ಏನಂದ್ರೆ πr² ಅಂತ. ಆ ಪೈ ಅನ್ನೋದು ಒಂದು ನಂಬರ್, 2, 3, 3.5, ಹಾಫ್ ಥರ ಪೈ ಅನ್ನೋದು ಒಂದು ನಂಬರ್ ಅದು. ಸೊ ಅದು ಫಾರ್ಮುಲಾದಲ್ಲಿ ಹಾಗಿರೋದ್ರಿಂದ ಅದು ನಾವು ಉಪಯೋಗಿಸ್ಬೇಕಾಗುತ್ತೆ. ಎಲ್ಲ ಸ್ಪೆರಿಕಲ್ಲು ಎಲ್ಲ ಇದನ್ನು ಅದು. ಸೊ ಆ ಫಾರ್ಮುಲಾದಲ್ಲೇ ಇದೆ ಅದು ಪೈ ಅನ್ನೋದು ಒಂದು ನಂಬರು. ನಾವು ಸ್ಕ್ವೇರು ಅದೆಲ್ಲ ನೋಡಿದ್ರೆ ಅದರಿಂದ ಅದೇ ಒಂದು ಬೇರೆ ವಿಷಯ ಆಗ್ಬಿಡುತ್ತೆ. ಅವಾಗೆಲ್ಲ ಅವಕಾಶ ಸಿಕ್ಕಿದಾಗ ಹೇಳ್ಕೊಳ್ಬೋದು ಅದು ಯಾಕೆ ಅದು ಅಷ್ಟು ಮಿಸ್ಟೀರಿಯಸ್ ಅಲ್ಲ. ಏರಿಯಾ ಆಫ್ ಎ ಸ್ಕ್ವೇರು ಅದರಿಂದೆಲ್ಲ ಏರಿಯಾ ಆಫ್ ಎ ಸ್ಕ್ವೇರ್ ಭಾಳ ಕ್ಲೀನಾಗಿ A² ಅಂತ ಗೊತ್ತಾಗ್ಬಿಡುತ್ತೆ. ಇಫ್ ಯು ಹ್ಯಾವ್ ಎ ಸ್ಕ್ವೇರ್ ಆಫ್ ಸೈಡ್ 2 centimeters, the area of the square is 4 square centimeters. So 2 square centimeters. 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 2 square c ಅದು ಏರಿಯಾ ಸರ್ಕಲ್ ಆಫ್ ರೇಡಿಯಸ್ 2 ಸೆಂಟಿಮೀಟರ್ಸ್ ಇದ್ರೆ ಏರಿಯಾ ಎಷ್ಟು ಅಂದರೆ ಆವಾಗ ಪೈ ಬರುತ್ತೆ ಅಲ್ಲಿ. ಅದರಿಂದ ಬೇಕಾಗುತ್ತೆ. ಇದು ವಾಟ್ ಇಸ್ ದಿ ಪರ್ಫೆಕ್ಟ್ ವ್ಯಾಲ್ಯೂ ಅಂತಿಲ್ಲ. ಅದು ನೀವು ಮಾಡ್ತಾ ಇದ್ದಂಗೆ ಇಂಪ್ರೂವ್ ಆಗ್ತಿದ್ದಂಗೆ ಮುಂದಕ್ಕೆ ಹೋಗುತ್ತೆ ಹೊರತು ಅದನ್ನೇ ಹೇಳೋದು ನಾವು ಮ್ಯಾಥಮೆಟಿಕಲಿ ಇಟ್ಸ್ ಎ ಟ್ರಾನ್ಸೆಂಡೆಂಟಲ್ ನಂಬರ್ ಅಂತ.
ಇನ್ಯಾರ್ದಾದ್ರೂ ಪ್ರಶ್ನೆಗಳಿದೆಯಾ?
ಇನ್ಫ್ಯಾಕ್ಟ್ ರಾಮಾನುಜನ್ ತುಂಬ ಮಿಸ್ಟೀರಿಯಸ್ ಆಗೋಕ್ಕೆ ಆ ಥರದ್ದೇ ಕಾರಣ. ಆಮೇಲೆ ನಾವು ಆ ಥರ ಸೀರೀಸ್ ಹಾಕಿದ್ರೆ ಅದೇ ನಾ ಹೇಳಿದ್ನ ಬರೀ ಸಾಮಾನ್ಯ ಜನರಿಗಲ್ಲ, ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ನೋಡಿದ್ರೆ ಸ್ವಲ್ಪ ತಲೆ ತಿರುಗುತ್ತೆ. ಏನಪ್ಪ ಇದು 1/π ಈ ಕಡೆ ಇದೆಲ್ಲ ಹೌದಾ, ನಂಬರ್ಸೇ ದೊಡ್ಡದು. ಆ್ಯಂಡ್ ಹೌ ಡಿಡ್ ಈ ಗೆಟ್ ದೋಸ್ ನಂಬರ್ಸ್ ಇನ್ ದಿ ಫಸ್ಟ್ ಪ್ಲೇಸ್? ದಟ್ ಮೇಕ್ಸ್ ರಾಮಾನುಜನ್ ವೆರಿ ಮಿಸ್ಟೀರಿಯಸ್ ಪರ್ಸನ್. ಹೌ ಕುಡ್ ಈ ಥಿಂಕ್ ಆಫ್ ಅಂತ ನಮಗೆ ಟೈಮೇನೆ ಕೇಳಿದರೆ ನಾವು 4:20 4:25 ಅಂತ ಹೇಳ್ತೀವಿ. ಅದು ಆ್ಯಕ್ಚುಲಿ ಅದು 24 ನಿಮಿಷ ಸಮ್ ಸೆಕೆಂಡ್ಸ್ ಆಗಿರ್ಬೋದು. ಅಫ್ಕೋರ್ಸ್ ಡಿಜಿಟಲ್ ವಾಚ್ ಕಟ್ಕೊಂಡಿದ್ದವರೆಲ್ಲ ಮಾಡ್ತಾರೆ. ಅದೇನೇ ಹೇಳ್ತಾ ಇದ್ದೆ, ಅದೊಂದು ತಮಾಷೆ ನೀವು ನೋಡ್ಬೋದು. ಮೊದಲೆಲ್ಲ ಟೈಮ್ ಕೇಳಿದ್ರೆ ಯಾವಾಗಲೂ ನಾವು 4:15 4:15 ಈ ಥರ ಹೇಳ್ತೀವಿ. ಈಗ ಎಕ್ಸಾಕ್ಟಾಗಿ ಹೇಳ್ತಾರೆ 4:24 ಅಂತ. ಯಾಕಂದರೆ ಡಿಜಿಟಲ್ 4:24 ಅಂತ ತೋರಿಸ್ತಾ ಇರುತ್ತೆ. ಅದೇ ನೀವು ಮುಳ್ಳಿದ್ದಾಗ ನೀವು ಆ ಥರ ಹೇಳೋಕ್ಕಾಗಲ್ಲ. ಸೊ ಇಟ್ಸ್ ಎ ಕ್ವೆಶನ್ ನೀಡ್ ಮೋರ್ ಆ್ಯಂಡ್ ಮೋರ್ ಇದು. ಸೊ ಅಲ್ಲೇ ಕಷ್ಟ ಅಂತಿದ್ದಕ್ಕೆ ದಿಸ್ ಕೈಂಡ್ ಆಫ್ ನಂಬರ್ ಇದು ಲಾಟ್ ಆಫ್ ಅಪ್ರಾಕ್ಸಿಮೇಷನ್ಸ್, ಆ್ಯಕ್ಯುರಸಿ ಅದೆಲ್ಲ. ಫಾರ್ ಎಕ್ಸಾಂಪಲ್, ಯು ಹ್ಯಾವ್ ಟು ಪ್ಲಾನ್ ಯುವರ್ ಸ್ಯಾಟಲೈಟ್ ಟು ಗೋ ಆ್ಯಂಡ್ ಲ್ಯಾಂಡ್ ಆನ್ ಮೂನ್. ಇಟ್ಸ್ ಎ ವೆರಿ ಹ್ಯೂಜ್ ಸ್ಪೇಸ್ ದೇರ್. ನೀವು ಇಲ್ಲಿ ಒಂದು ಸ್ಮಾಲ್ ಮಿಸ್ಟೇಕ್ ಆಫ್ 1,000th of a millimeter, that rocket will miss the moon by several thousand kilometers. Instead of going to moon, it will go somewhere else. You notified, I mean, the ISRO thing which was streamed live, you saw there was some small error, so which meant it did not calculate the height properly, so it crashed instead of landing soft. So all this happened because of calculation mistakes. Yeah, I mean that's one good example. Yeah.
ಯಾರ್ದಾದ್ರೂ ಪ್ರಶ್ನೆ ಇದೆಯಾ?
Yeah.
So this is Janvi. So if pi don't have perfect value, then whatever areas we'll get, no sir, it also don't have perfect value, no sir?
Yeah, it's an approximation.
Oh, okay.
It's an approximation. Okay. That's why I said that's where the problem might come between two people. If there was the exact value, there is no fight. But you may say mine is a better value, mine is a better value. So the government should declare for India, this is the value of pi.
Okay, sir. Thank you.
ಇಲ್ಲಿ ಅಜಿತ್ ಇಕ್ಬಾಲ್ ಸಿಂಗ್ ಅನ್ನೋರು ಒಂದು ಪ್ರಶ್ನೆ ಕೇಳ್ತಾರೆ. How could Srinivasa Ramanujan do so much work in short span of his life? He applied the function of arc, tan to write his series.
Since she is a mathematician, I can tell it connects two different things in mathematics in a different way. 1/π and what are called elliptic integrals. So you simplify it in two different ways. In one way you get 1/π. If you simplify it the other way, you get that infinite series. So it's associated with algebraic number theory and things like that. And that is the thing. So that is the example I am giving for Ramanujan's vision. What do we mean by vision? Means I am standing in Bangalore and I am just looking up north and I say there are snow-clad mountains there. I can't see, nobody else can see. But that's what we mean by vision. So then others will have to verify. Oh, you will be just telling something which has come to your head. Let's go and see. Then they go and actually see that there is a mountain. Then people will wonder, how did he see it when we can't see? That means he has some special kinds of abilities.
ಇನ್ಯಾವುದಾದ್ರೂ ಪ್ರಶ್ನೆ? ಐ ಥಿಂಕ್ ಯಾವುದು ಇಲ್ಲ ಅಂತ ಅನ್ಸುತ್ತೆ ಸರ್. ಥ್ಯಾಂಕ್ ಯು ವೆರಿ ಮಚ್ ಫಾರ್ ಯುವರ್ ವಂಡರ್ಫುಲ್ ಟಾಕ್. ತುಂಬಾ ಸಂತೋಷ ಆಯ್ತು ನೀವು ಬಂದು ರಾಮಾನುಜನ್ ಬಗ್ಗೆ ತಿಳಿಸ್ಕೊಟ್ಟಿದ್ದೆ. ಥ್ಯಾಂಕ್ ಯು ವೆರಿ ಮಚ್. ಥ್ಯಾಂಕ್ ಯು. ಇದೇ ತಿಂಗಳ 22 ಶ್ರೀನಿವಾಸ ರಾಮಾನುಜನ್ ಅವರ ಜನ್ಮದಿನದಂದು ಶ್ರೀಯುತ ಹಿರಿಯಣ್ಣ ಅವರು, ಸೈಂಟಿಸ್ಟ್ ರಿಟೈರ್ಡ್ ಫ್ರಮ್ ಇಸ್ರೋ, ಇವರು ಗಣಿತ ಸಂವಹನಕಾರರು ಕೂಡ. ಇವರು ಎನ್ಚಾಂಟಿಂಗ್ ಮ್ಯಾಥ್ಸ್ ಇನ್ ಎವ್ರಿ ಡೇ ಲೈಫ್, ನಿತ್ಯ ಜೀವನದಲ್ಲಿ ಮೋಹಕ ಗಣಿತ ಅನ್ನೋ ವಿಷಯದ ಬಗ್ಗೆ ಮಾತನಾಡಲಿದ್ದಾರೆ. ಡಿಸೆಂಬರ್ 22, ಈ ತಿಂಗಳ ಡಿಸೆಂಬರ್ 22 ರಾಮಾನುಜನ್ ಅವರ ಜನ್ಮದಿನದಂದು. ಎಲ್ಲರೂ ಹೆಚ್ಚಿನ ಸಂಖ್ಯೆಯಲ್ಲಿ ಭಾಗವಹಿಸಿ ಅಂತ ಕೇಳ್ಕೊತಾ ಈ ಕಾರ್ಯಕ್ರಮನ ಮುಗಿಸ್ತಾ ಇದ್ದೀವಿ. ಥ್ಯಾಂಕ್ ಯು ಸರ್, ಥ್ಯಾಂಕ್ ಯು ಒನ್ಸ್ ಅಗೇನ್, ಥ್ಯಾಂಕ್ ಯು ವೆರಿ ಮಚ್.